Hello. So first, I'm going to talk about the cell and the cell bodies. First, we have obviously the dendrites here and the nucleus. This is the soma. This is a cell body. This is the axon hillock. This is the axon. Here is the axon terminals. These would be the synapses and the gap junctions here that allow the neurotransmitters to come through into the cell. And this is I don't know if I said this axon hillock here. This is the presynaptic neuron that is sending the signals, and this is the postsynaptic neuron that is going to be receiving the signals. I think I got everything there. Okay, so I'm gonna try and do my best on this. I'm still not 100%, but I think I've got most of it. So the neuron starts off in a resting state, which is the negative 70 millivolts. Then the signals start coming in through the axon hillock um, that cause voltage gated sodium channels to reach the threshold, which is negative 55 millivolts here. Then the neuron then depolarizes because it's got all of the sodium coming in. So it's depolarizing. Um, and the depolarization moves down the axon and it jumps from node to node, node of Rambier to node, at a constant speed. It does not stop. It's called the all or none rule, where when the axon starts firing, the action starts, it doesn't stop until it goes all the way through. The potassium then reaches its threshold, and those channels open more slowly than sodium channels. So repolarization starts to happen. And when we're in this section here, that is called the absolute refractory period. That means that another actual action potential can't happen because there's already one happening. Um, so then the depolarization, or sorry, the potassium then reaches its threshold, but those channels open more slowly than sodium channels, so it's slowly going down. Um, the potassium leaving causes repolarization. The depolarization and subsequent repolarization is the action potential. The action potential is jumping from node of Ranvier to node. It flows down at one speed. The action potential causes voltage-gated potassium channels to open at the terminal buttons, um, which causes exocytosis. The neurotransmitters float across the synaptic gap here into this cell body, and they fit into the receptors of the postsynaptic, this here, postsynaptic neuron. The receptors either open directly and are ionotropic receptors, or they go through a second messaging system that the metabotropic receptors require. The neurotransmitters can cause an excitatory signal or an inhibitory signal. Excitatory would urge the signal to carry on, and inhibitory would eventually stop that signal from firing. Um, Lastly comes the potassium pump that cleans out the sodium and brings the neuron back to the resting state of a negative 70 millivolts. Reuptake happens also where the cell is cleaned out to receive new neurons, and if not, the neuron will flood and you'll have feelings of confusion. It could result in that. I talked about the absolute refractory period. Um, There are ESPS, which is excitatory postsynaptic potential, and then inhibitory postsynaptic potential, which I talked about, where can either excite the firing or inhibit the firing of neurons. So it can either keep it going or stop it. And then also summation. So there's spatial summation, where, sorry, 1 second. 1 second. There's spatial summation. Of course, I lost it. Where several synapses having a cumulative effect on the rate of the action potential. Lots of synapses with incoming ions collected at one time. So that creates the neuron to fire faster. Or there's temporal summation, where a cumulative effect of many signals in a short amount of time. One signal comes in, and then right after another signal comes in, and if calculated at the same time, then all those signals will be included, and it will be able to fire. Um, I think that I've got everything. Thank you so much.